When we're estimating a simple linear regression model, it's often going to be useful for us to think not only of the slope parameter estimate, but also of a confidence interval around the slope parameter estimate. This is going to give us a sense of what is the range of plausible effects that the explanatory factor might have on our outcome. This is going to give us a range that we can make decisions over and think about the association between these two variables. But in order for us to think about confidence intervals for the slope parameter estimator, we have to think about the sampling distribution and how we can use that to quantify the uncertainty within that estimator. Now, because the slope estimator has a normal sampling distribution, we're going to be able to use t-based confidence intervals and standard t-based confidence intervals at that in order to fit a confidence interval for the regression parameter. So what is the slope estimator? How can we think about it? Well, we take beta hat 1 to be the ratio between the sample covariance Sxy and the sample variance of x, which is Sx squared. This is going to give us an estimate for beta 1 in a simple linear regression model. Now, if we either have normally distributed random errors, or the sample size is sufficiently large, then what we can say is that beta hat 1 is going to be normally distributed, approximately normally distributed if we're relying on large samples, according to a normal distribution with a mean of beta 1 and a variance of sigma squared times by 1 over the sum of xi minus x bar squared. Now, using this sampling distribution, we're going to be able to come up with the confidence interval formula for beta 1. If we standardize this, then what we can do is come up with a t-distribution. Now, when we're standardizing, we're using the estimated standard error of beta hat 1, right? So that's going to be taking the square root of this term, but instead of us using sigma squared here, which is unknown to us, we're going to plug in the mean squared error, right? So if we plug in the mean squared error here, then that's going to give us the estimated standard error of beta hat 1, and then standardizing using that estimated standard error is going to give us a t-distribution with n minus 2 degrees of freedom. And so this t-distribution is going to serve as the basis for our confidence intervals here. So we can form confidence intervals for beta 1 using this t-distribution. What do those confidence intervals look like? Well, we'll look at the standard two-sided symmetric confidence interval. So if we want a confidence level of 100 times 1 minus alpha %, we take beta hat 1 plus or minus our critical value times by the standard error of beta 1. Okay, so this is going to be our standard form for the two-sided symmetric confidence intervals. It's always our point estimate plus or minus the critical value times by the standard error. Okay. If we fill out what this is sort of explicitly, that's going to be beta hat 1 plus or minus t n minus 2 alpha over 2. That's the critical value from the t-distribution. And then that's the estimated standard error. So we have the MSE plugged in, and otherwise that's the square root of the variance term that we saw in the last slide. This is going to be the format for any two-sided symmetric confidence interval. So it's always the point estimate plus or minus the critical value times by the standard error. And in this case, we just simply plug in all of the values that we have from our sampling distribution here. Now, if we happened to know what sigma squared was, then what we can do is we can replace this MSE with sigma squared, and we can replace our critical values with z alpha over 2. Now, it's very unlikely that we'll actually know sigma squared, and so almost always we're going to be thinking about the t version of this, but if we did, then that could be replaced to get a standard normal-based confidence interval. We can also fit analogous intervals based on one-sided or asymmetric confidence intervals, and the way that that's going to work is simply choosing a different critical value. So based on whatever actual confidence level we want, whether that's going to be one-sided or asymmetric in some other way. Now, often, the standard error of the parameter estimate is actually going to be output by statistical software, which is going to prevent us from actually needing to take on this format here. Right, so very often we're going to be able to look at our statistical software and we're going to be able to use this form for our confidence interval directly. So we'll take beta hat 1 plus or minus our critical value times by the estimated standard error. And that's going to give us the confidence interval that we're interested in. Now, the relevance of this confidence interval is going to be contingent on that linear model being correct for the conditional mean. So what we mean here is that if linearity does not hold, then it's not going to make sense for us to think about the confidence interval for beta 1. Right? If we do not have a linear model that's going to be relevant for us here, then we're not going to be thinking about the confidence interval as being particularly relevant. But when that linearity assumption is reasonable, then we can use those confidence intervals to do inference on that parameter. So we can take a look at some examples here. And in these examples, we're thinking about taking our output directly from statistical software. So this first example, we're looking at a rehab clinic, and they want to determine the relationship between the number of hours a patient spends in physiotherapy each week and their improvement in a standardized mobility score. So they collect data on n equals 100 patients and obtain the following regression output from software. And so in this regression output, we have our characteristics, we have our beta estimates, and we have our standard error estimates. Our characteristics are going to be our intercept or therapy hours. So therapy hours is actually going to be our predictor variable in this model. And then we have our estimated values for beta. So that's going to be beta hat 0 is 5, beta hat 1 is 2. And we have our standard errors for beta hat 0 and beta hat 1. And those are the estimated standard errors. We're also told some extra information, right? So we're told the number of observations is 100, though we were given that in the text of the question. We're told that sigma is 2.91. And so sigma in this case is going to be our square root of the MSE. Okay, and so if we take sigma, that's going to be sort of approximately the square root of the MSE in general. And so then when we're thinking about the sigma that we have, that's actually going to be the square root of the MSE here. And then we're also told that the R squared value is going to be given to us by 0.753. Okay, so we're told all of this information, and what we want is a 95% confidence interval for our slope. And so remember that this confidence interval is always going to take the form of our point estimate plus or minus our critical value, and that critical value is going to be the Tn minus 2, alpha over 2, critical value, and then we multiply that by the estimated standard error of our value here. Okay, and so in this case, right, we can take alpha is going to be 1 minus 0.95. That's going to give us 0.05 for our alpha here, right? And we can work out, well, what is the standard error is going to be 0.114, right? Our estimate value here is 2.0, okay? And so then we just need to plug in our critical value, and that's going to end up giving us this confidence interval here, right? So we can walk through how we can do this sort of exactly using the output here. So we get n is equal to 100, and so the sampling distribution is going to be based on a Tn minus 2, which is a T98 distribution, okay? Alpha is going to be 1 minus 0.95 or 0.05, and so the critical value is going to be 1.984. And so if we want that critical value, we can use R to get it, right? Qt is going to give us the critical value from the T distribution. The level is 0.05 divided by 2. The degrees of freedom is 98, right? So that's going to output that 1.984 here. So then to get our confidence interval, right, we're going to take beta hat 1 plus or minus the critical value times by its standard error. So that's going to be 2 plus or minus 1.984 times by 0.114, right? Drawn everything from the table right here. That leads us to 1.774 to 2.226 as our relevant values for the confidence interval here. Have our second example here. This researcher is interested in exploring the relationship between an individual's level of extroversion and their score on a standardized social anxiety assessment. In a sample of n equals 50 individuals, they received the following output. So once again, we can look at this table, right? And we're ultimately going to want a 99% confidence interval for our slope. And so we're most concerned with this row from our table here, where we're told that the estimate is negative 3.7 and the value of the standard error, the estimated standard error, is 0.343. Again, we can see the other information that we need, right? And if we had wanted to do something using the intercept, we could have used this top row here, right? But so we want the 99% confidence interval. And so in this case, we're going to find that alpha is going to be 1 minus 0.99. So that's going to give us 0.01, right? And then our confidence interval is beta hat 1 plus or minus the critical values. That's a Tn minus 2 alpha over 2 times by our standard error of beta hat 1, okay? And so plugging in all of our values there is going to lead us to the estimated confidence interval. And so we can work through that in this case here, right? Take n equals 50, so our T distribution is going to be a Tn minus 2, our T48 distribution. Alpha is going to be 0.01, and so our critical value is going to be or 2.682. Right? We get that out of our Qt function here, right? 0.01 over 2 is the value that we want. Degrees of freedom is 48, and so that's grabbed directly from R there. We can then plug everything into our confidence interval formula. So we take our point estimate plus or minus the critical value times the standard error. That gives us negative 3.7 plus or minus 2.682 times by 0.343. And that's going to give us this interval from negative 4.62 up to negative 2.78. And so that's our 99% confidence interval for the slope parameter in this regression model. So by using the normally distributed sampling distribution, we can use standard t-based confidence intervals for the slope parameter in a simple linear regression model. Right? If we knew what the population variance was, we could use our standard normal confidence intervals, but typically that's not going to be known, and so instead we're going to rely on the estimated standard error. Fortunately, most of this information is going to be able to be output directly from regression software, and so then it's just going to be a matter of knowing exactly what inference we're trying to do, and then actually extracting the correct information and plugging that into the relevant formula so that we can conduct the inference regarding the parameters in the models that we actually care about.